So last time, we analyzed linear regression, okay, and then obtained a bound for this quantity, okay, and so if you recall, under the linear regression model, so we assume, for example, that the regression function is linear, and then we made another assumption, which was this conditional variance of y given x is equal to x. This is sigma squared. Okay, and so given these two assumptions, we showed that this is basically sigma squared x transpose x inverse x. Okay, and we wrote it like this. And I call this quantity sigma hat n. And the interpretation was that this can be written as 1 over n summation I from 1 to n xi transpose, and so we call x was x1 transpose up to xn transpose. And so by the law of large numbers, this converges to sigma, which is just the covariant, like it would be like the expectation of one of them, x1 transpose. And if xi's are assumed to be IID from the marginals, they're assumed to be IID, but if the marginal distribution has zero mean, so if let's say P of x, the marginal distribution of x is zero mean, then this quantity is the covariance matrix. Covariance matrix of the distribution P of x. Okay, so the assumption is that this is going to converge, or this part is going to converge. So this is sigma hat n. Okay, and with high probability, it's going to be close to sigma. So what I'm going to do is I'm going to write, so for large and approximately sigma squared over n, x transpose sigma inverse x. So that's how it behaves. Sound good? So if you let's say assume, so this sigma squared is the variance of the noise. This conditional variance is some sort of a noise. Let's say if you assume in a very simple case, it's a simple example, that, for example, this sigma is identity. So the sigma is like the covariance of this in the coordinates. So it's like the coordinates matrix of the t-shirt. If that's identity, let's say each coordinate is independent of the other ones, and we have all the same variance, which is I. So that would turn into So this quantity, maybe I'm going to call it m of x in the notes. So this is like mean squared error of sort that we calculate. It's going to be approximately sigma squared, and sigma inverse goes away, so you get x transpose x, or rather sigma squared over n, the norm of x squared, so the L2 norm. And for example, if x is negative infinite, like negative 1 to 1 to d, so this is saying that each coordinate of x is between -1 and 1, then we can upper bound this. So if each coordinate, so this is saying basically, if I have a single x like this, xi is less than or equal to 1 for all I from 1 to d. So if I have an assumption like that, is there an upper bound with upper bound? It's fine. So this is the sum of the squares of xi's, okay? What is the largest that it can be? Okay, that is louder.
Oh, is it one because it's square of one, and that's the large.
Yeah, but this is like multiple. So this is like sigma xi squared I from 1 to d. D. Okay, so a good upper bound is d. So what we get is sigma squared d over n. Okay, so you can see how the dimension appears. You can sigma squared d over n. If we do the partitioning estimator, so let's say this is for the linear estimator. If we do our partitioning estimator, we argued, if you go back, that this would look like sigma squared over n divided by 2 plus d. Okay, so this is a manifestation of dimensionality. This is sort of fine in comparison. Okay. The reason is that you can see the d appears in the power. Okay, so the rate changes. So instead of like 1 over n, if, for example, e was, let's say, 0, this would be sigma squared over n. But if e, I mean, the 0 doesn't make much sense. But if it's like very large, you get 2 over something which is very large. So this is going to be pretty close to 0. So you get 1 over n to some fractional power, which is very small. And so this goes down very slowly. Whereas the rate here, so if d, for example, is 10, this is still like sigma squared over n times 10. But this is going to be, for example, if d is 10, then this guy is going to be approximately upper bounded by sigma squared 10 over n. So the rate is still goes down like 1 over n. So you get a factor, which is problematic. But as it gets large, you don't worry too much. But this guy is going to be sigma squared over n to the 2 over 12, right? Which is 1 over 6. Okay, this is really bad because now I need so in order to like get something like that, I need n to the power 6 to get something like this. Right? So the sample size here, the amount that it can go down for a given n, in order to have the same amount here, I have to raise n to the power 6 to combat this 1 over 6. So I have 100, like, let's say I have 1,000 samples here. This is like the sigma squared. You get the same thing that has to raise this to the power, like 1,000 to the power 6, so we need that whole chunk. And that is flat, okay? So these estimators are good, but if the actual function is linear, this is gonna converge very slowly. We're not gonna use this in practice. So the ideal thing, so the whole point of these kind of exercises is to convince you that if you assume a parametric model, and if the parametric model is correct, or a good approximation of truth, then you can learn it much faster. And if you don't assume anything, you have an estimator which works. Let's say for a very general class, we showed this for a literature class. If you go back. But the price that you pay is a very slow rate. And yeah, and you can maybe go back. This was like an upper bound, as was pointed out. So we did an upper bound on the bias part. So as a target case, this is a good thing. But for the bias, we had an upper bound. But in the linear case, you can go back and check that the upper bound is quite tight. So the bias is actually, so we did something like that. If you remember, there was like L squared, HS squared was the bias plus sigma squared over N HD. I didn't do that high dimensional case, but this was easy to use with limited size. No, so this was an upper bound, but in this case, you can go and check that this is actually tight upper bound. If you have a linear function, you pay this much price, but L is going to be the norm of theta star. So you can't say, okay, this is the big part analysis. If you do this, maybe then better off a faster that you pay. So a similar thing extends to some of the other, for example, like the k-nearest neighbors. For the kernels, like the smooth kernels, things are a little bit different. So this is just a function against them. And then usually the variance, the law of the variance is you don't get enough points in each partition. Okay. Good question. Maybe show you later what it looks like the partitioning is in this case. Questions, comments? Okay, so let's go back maybe. So what we did was to sort of talk about the general framework of empirical risk minimization. I replaced the expectation and the risk with empirical expectation. So this was the risk. And we replace it with the empirical expectation. It would be this quantity, right? And then I would have an optimization problem, and then we restrict our class of functions to a certain smaller class. And in the regression case, what we did was so the loss is quadratic. I get that. And then the function class is linear, so I get this. And then I want to optimize, this is an optimization problem. I have to find a function here. So in this case, it would be to find this theta. And so you plug this into that formula, and you get this problem, right? And in this case, because quadratic loss is pretty simple, we can actually solve for the solution. So you take the gradient to equal to 0, and by the general sort of analysis argument that this is a convex function, you can also verify that it's actually like the solution, but these are usually the station points. Okay, so when you set the gradient equal to 0, there is no guarantee that the solution is a minimizer. Could be a maximizer, could be a saddle point. But in this case, there is no such thing as maximizer or saddle point, so you just have a minimum shape function. And so you can, otherwise, you can compute the second order derivatives with the Hessian and verify that's positive semi-definite. Okay, so that's what we did, and then we can use this closed form formula to do the analysis, and that's what we did. What I want to do is like introduce a more general idea, which you may have already know. Or you may already know, or may have already have seen. To solve opposition problems like this, where we don't have a closed form. Okay, and then we move to the classification version of this, for which we don't have a closed form. So what is the general like approach to solve an optimization problem like this? If the function is more complicated, then it's whatever it is here is a more complicated function of theta. Is there like a numerical approach that you know? Gradient descent. Okay. Any other people have heard about gradient descent? So what is gradient descent? Yes.
It's essentially taking the negative of the gradient to go calculate it at each point to reach the bottom of the function.
Right. Okay. Right. So the idea is that at each step, so start from an initial give. Look at the gradient of the function at that point. The gradient points to a direction. I'm going to go to the opposite direction. I'm going to take one step in the opposite direction. I land at the new point. Compute the gradient, points in the direction. I'm going to move in the opposite direction. So why are we moving in the opposite direction of the gradient?
Because the gradient is pointing to the highest.
Right, the gradient points to the direction of maximal descent, in a sense. So you want the opposite is actually the direction of the most descent. Okay, so these are like ideas from calculus if you review. So gradient descent. Okay, so we can do it in 1D, but let's do that more general. So if I want to sort of minimize, let's say, f theta, let's say theta in RD, this is a nonlinear function. So the gradient descent does something like this. So you have an estimate at time t, and then you have the gradient of the function at time t. And there's a step size, so I'm going to multiply by some, usually a small number, and then this is the negative direction. So I added the data. This gives me the new data point, or new estimate. So different ways of motivating this approach. One way of motivating it, which I kind of like, is if you do the Taylor expansion of the function, let's say around point f theta, so theta p. So anyone knows what the first order Taylor expansion of the function would be? Taylor series. So it looks like this, the inner product of the gradient theta minus that. So, and then there are other variants. So the idea is roughly that we are trying to minimize this linear approximation. So if you look at this part, this is really a linear or affine function. So this is a constant because it says we are looking at a specific theta of t, and this is a constant, The only variable is the theta. And so if you look at this, this is of the form, let's say b plus a theta minus, I don't know, theta naught. Okay, so this function as a function of theta is linear defined. And so if I try to minimize it, minimizing the defined function, it's easy to see that I have to move in the direction of negative a. So by sort of Cauchy-Schwarz, let's say this thing is going to be between negative norm of the gradient. Okay, let's not do that, but yeah, if you do Cauchy-Schwarz, you would realize that this quantity is upper bounded, and the maximum happens when this is in the direction of that, when this is in the opposite direction. So do the Cauchy-Schwarz equation. And so this is very intuitive. So once you do this, you realize that inner product two vectors is minimized if this is negative in the direction of this. This is the norm. Ignore the norm to look at the direction that minimizes this is negative. As you can think of the gradients and as sort of minimizing a first order approximation of the function. If you sort of follow this, you can try to add the quadratic and try to minimize that. The quadratic model function that would be like a Newton's approach to but this idea is just linear approximation, trying to minimize it to this idea of gradient descent. Of course, I can't minimize this perfectly because what happens if I try to minimize this function? Or all RE. So imagine like in a univariate case, you would have, say, have a function like that. This is a point theta t. This linear approximation is just a line. Random line. Okay. And here in the univariate case, there are just two directions, either in the direction of the gradient or the opposite. So this is the direction, the gradient points in this way. And because that's, if I move in this direction, the function goes up. If I move in the other direction, it goes down. So I can move in the opposite direction. So theta move, if I move in this the direction, let's say the gradient, let's say you can think of it as operating in the space of theta. But what if I try to minimize this function, what we have for the RD?
The approximation is not bounded.
Bounded, you go to the negative state. So I can't really minimize it. If it was quadratic, it actually can minimize the entire thing. Because let's say the quadratic approximation would look like this, maybe. So there is a minimum, but this linear function doesn't have a bound, so you don't want to move all the way. Because if you also like move, first you can't, it's unbounded. If you move all the way, so your approximation is very bad. So you're gonna take just a very tiny step. Now at this point, my gradient is gonna be, so if I move a little bit, my gradient here is gonna be different, right? So now, let's say I move just a little bit, now my gradient is like that. Still points in this direction. So in univariate case, it's just the direction is either this way or that way. There's no much room. So you still move in this direction. And eventually you hit here, which is in this case, it's the gradient is 0. So as you approach this location, the gradient and the norm gets smaller and smaller. So you take a smaller and smaller step to start converging to the minimum, which is in this case 0. Okay, so it's built in naturally. This convergence is built into it if you take small steps. Small steps. We don't try to prove it, but on the general condition, you converge to a point where the gradient is 0. Right. Yeah. So you find the stationary point of the function. And if the stationary point happens to be a minimum, then you win. In the convex case, when the function is convex to an example convex function, there's going to be an interval for the unit conversion. Sounds good. Okay, so that's the idea of gradient descent. And you can do this to many complicated functions as long as you can take a gradient Okay, so you're gonna have to be able to solve, but this is effectively solving this equation, like tries to solve for a theta whose gradient is 0. So the effective thing is that you can see as if this converges, theta t is going to be equal to theta t plus 1. So these go away, and you get the gradient of theta is equal to 0. If it converges for point of view. And sort of that's a general approach to solving first order automatic and then convergent. Does that make sense, people? Right. So I can do this optimization by just calculating the gradient. We actually did the gradient here. So that's my gradient, right? So what would happen here is that if I write for let's say for a regression problem, the gradient of f of theta is, so f of theta is 1 over n summation I from 1 to n yi minus xi transpose theta squared, which is also 1 over n y minus x theta squared. So I do the gradient. The gradient would be 1 over n x transpose xy minus x theta minus y. And my gradient descent would be like theta t plus 1 is equal to theta t minus mu times this quantity xt theta t minus y, something like that. Yeah. Okay, so you get very simple update, and this actually solves that those normal equations. So you don't have to do the inverse of the matrix x transpose x, it's automatically sort of it's another way of like calculating the inverse of the matrix. But it doesn't have that costly operation. So double check the gradient. Okay. Sounds good. So I just want to show you how you can do this in so there's this package called PyTorch in Python, and it's a very popular package for people that do deep learning AI, sort of what they call AI now, or machine learning. So the main advantage is that if you compose this function in a certain way, you don't have to calculate this gradient by hand, because if it's like a composition of functions that you already know, and you know how to depict the gradient, then the computer can automatically take the gradient for you. So that makes it very convenient. So you build up a lot of, like there are a lot of building blocks already like implemented. So for example, if you have a quadratic loss and then you have this linear function, so all of this, the gradient is known. So you just set up your loss function and you track what kind of function of theta it is, and then knows how to take the gradient. So you just do a simple command, and whatever complicated model you constructed, you can calculate the gradient automatically. So the one that I was trying to show was, so let's say my f theta, or the loss, is theta. I'm already theta 1 squared plus theta 2 squared. So Python is 0 based. So start at 0, but so theta is 2-dimensional. So the contours are, or level sets. So level sets or contours of f are so for any like the level set, like there's a parameter. So let's say level equals c if you want, is a set, or level c is a set in the theta domain, so theta 1, theta 2, such that if theta is equal to c. Okay, so for example, level, let's say 1.5 is the set of all theta 1, theta 2, such that theta 1 squared plus theta 2 squared. Let's say do 4. 4 is going to be 4. Okay. So it's the location of all points such that theta 1 squared plus theta 2 squared is equal to 4. And what is this shape? Circle, yes, the circle. So it's certain, it's like it's centered at 0, and then you have like a circle of radius 2. I can plot it. Maybe if I hold it, it would be a circle. Yeah, okay. Good. So that's what you get. And something like that. And right here. Yeah. Right. The circle of radius 2. So what happens if I do like level set 1? So we still would circle, but a different circle, right? So it would be what would it be? Paste. And then maybe I'm going to color it to be like blue because smaller, and then the radius is going to be smaller, so it would be something like that. Okay, and so you do the different level sets, and you get a different circle every time in this case. Theta 1, theta 2, such that theta 1 squared plus theta 2 squared. So and then I get these concentric circles, right? And you color them to show those spots that they have. You color the base on their levels. For example, the smaller levels would be like blue, and then the larger would be red. So the way of visualizing like how sort of high the function value is. So as you descend, you're on smaller levels. And then the gradient will be orthogonal to these levels. It's not hard to see in this case, because the gradient is, in general, you can like, how can we prove that the gradient is orthogonal? Is there a way to prove that the gradient is orthogonal to the level sets? Is it possible? So in this case, gradient of f is 2 times theta 1, theta 2, and you can see that in terms of the direction, it's pointing this way, so along the 45 degrees everywhere that you are, and matches the direction. I think the one way of proving it is if I look at this function. Right. So can I say if I take the gradient of this, this is 0, right? Okay, it's going to be a little tricky. Let's not worry about it. But we can try to prove it because the level basically. So the intuition is if there is a component of gradient along the level, so if I move along that direction, I am going to change the function. And so I can't, that can happen because the function is constant. So when I move along the normal says a little bit, the gradient has to be zero. Like the component of the gradient along that direction, the direction of the gradient has to be zero. So if you have a direction, take the gradient and so gradient of f theta, like inner product with the direction a gives you like the directional derivative function along the a. And so along the a, which is like tangent to this should be zero. Because otherwise we would change the value of the function, so that can't be the but it's like that. But to prove it, you can try to like do the argument. So all this good, right? So now we have a machinery which is pretty powerful, and I can now like not worry about the complexity of the model or the loss function. Just still have to worry, but much less worrisome. I can just think about a more complicated model or more say not necessarily closed form tractable models, and just plug into the machinery of gradient descent and do the empirical Ross minimization. So empirical Ross minimization with a procedure like gradient descent would like open up a lot of possibilities. So what I want to do next is tell you like the equivalent. So what is the equivalent of the like equivalent or counterpart linear regression for classification. And there are different versions of this. But we saw that if you assume that the function is linear, and if the function is actually linear, then approximating by linear function is much better than trying to do these more generalized things. So we want to do that for, let's say, classification. The issue with classification is that they're twofold. So if I, for example, start from the empirical loss or like training loss, imagine I have 1 over n summation I from 1 to n here, it would be the 0, 1 loss. So I have something like that. I want to assume that if I, let's say, there are multiple issues. So I can like naively assume that I'm going to look at all the f's such that f, or like f thetas basically, of the form f theta equal theta transpose x. So this immediately causes some issues for some theta. Okay. Anyone that can see like the immediate issue with this? I want f to be like 0, 1 value. Right? So this is not 0, 1 value, and it's actually unbounded. Okay. So if you remember, like our like optimal solution was like f star was something like 1 if eta of x is bigger than 1/2, 0 if eta of x was less than 1/2. And at the boundary, it doesn't matter. If you did the exercise, you can define it whatever you want at the boundary. So what happens is, because these functions can't be linear, like in the stream function. So maybe I can like look at eta and try to work out something about eta. Maybe eta can be linear, and then I can threshold. So maybe let's model eta, which is the regression function in this case. Still expectation of y given x, but it would be the probability of y equal 1 given x. So at least this is not discrete, right? But there's also a problem. You can't just say this thing is of the form. So can you say eta of x is of the form theta transpose x, like the way we did in the regression case? That doable? Is it reasonable?
Because it would be it wouldn't be a probability then.
It's not a probability, yeah, so it could be negative, it could be one much bigger than one, so this is not. We know that this is not necessarily good, because you can try it, but, you know more about data, you know that it's probably, so you wanna like encode that into the form of data. Okay, so you want it to be sort of linear, but, it can't be a linear function of x, so no linear function of x behaves like the probability, because it has to saturate at one, so linear is sort of always. Maybe. So what is the solution? So this is not good. The simplest solution is, are you seeing the simplest solution? So just compose it with a function that maps like the GLs to 0 to 1. And you're done.
Use logistic regression.
Yeah, so you can, I'm trying to build logistic regression. So what you can do is like you can apply a function, whatever function you want, right, that maps the real value. So this is real valued, problematic. I want something with 0, 1. So I can map it to 0, 1 by a function that maps the real values to 0, 1, something like that. Any function can do actually, but what people usually work with is something which is smooth and negative infinity gets very maps to 1, positive infinity maps to, sorry, negative to 0, this maps to 1. So it saturates. So it's guaranteed to be linear and 1. Again, you can take this to be anything like this, or actually you can define it more complicated, but if you take it to be this particular function, eta, let's say t is 1 over 1 plus e to the negative t, they call it logistic regression. The model that we get, the modeling the regression function like this with that form is called logistic regression. So this is a simple solution that we can do, and it's sort of equivalent to linear regression. Okay.